Good afternoon to all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the video lecture series on linear time invariant systems using Fourier transform and Laplace transform. See, linear time invariant systems are characteristic with the help of differential equation, impulse response, block diagram, state variable description, transfer functions. It is used to represent continuous time linear time invariant system. It relates the input and output of the system. When x of t is applied to differential equation which can produce as the output as y of t. What is mean by system transfer function? It is the ratio of output to the input. H of s is equal to y of s divided by x of s. Frequency response, s can be replaced by omega. We can get the frequency response. H of omega is equal to y of omega divided by x of omega. When x of t is applied to Fourier transform, we can get x of omega. From frequency domain analysis, we can get the output as y of omega. While we applying the inverse Fourier transform of y of omega, we can get the output as y of t. Impulse response. Impulse response is the output generated by the system when the unit impulse is applied at the input. X of t is equal to del of t can be applied to linear time invariant system which can produce output as h of t. H of s is equal to y of s divided by x of s. How to find the impulse response? By taking inverse Laplace transform of h of s. Fourier transform. See, Fourier transform can be applied for both periodic and non-periodic signals. It can be represented only in frequency domain. It provides the effective reversible transformation link between the frequency domain and the time domain representation of these signals. The spacing between the spectral components becomes infinitesimal and hence the frequency spectrum appear to be continuous. It has a periodic signals has fixed period t0. This is the Fourier transform. While we applying the time domain to frequency domain, we can using the analysis equation. For converting frequency domain to time domain, we can using the synthesis equation. S of t and S of s forms the transform pair. Laplace transform. Laplace transform represents continuous time signals in terms of complex exponential, that is nothing but e power minus st. Laplace transform can be used to analyze signals or functions which are not absolutely integrable. Continuous time signals can also be analyzed effectively using Laplace transform. Laplace transform of the impulse response is called system function or transfer function. This is the time domain into frequency domain. When x of t is applied for Laplace transform, it can produce x of s. H of t for Laplace transform, h of s. Therefore, y of t is equal to h of t into x of t, which can produce y of s is equal to h of s into h of s. How to find the impulse response of the system? For the differential equation, we can apply the Fourier transform and then form the algebraic equation solving for roots. Finally, we can take the inverse Fourier transform. We can get it as your impulse response of the system. This is the basic signals as unit step signal, impulse signal, ramp signal. U of t is equal to 1 for t greater than or equal to 0 for unit step signal. Impulse signal 1 for t is equal to 0, 0 for t should be not equal to 0. R of t is equal to ramp signal t for t greater than or equal to 0, 0 for t less than 0. The graphical representation can also be given for basic signals. Now we can find out the Fourier transform results. The differential equation is given as d square by dt square into y of t plus 5 into d by dt into y of t plus 6 into y of t is equal to minus d by dt into x of t. Determine the frequency response. By taking the Fourier transform of above function, we can get it as your j omega square into y of omega plus 5 into j omega into y of omega plus 6 into y of omega is equal to minus j omega into x of omega. Now we can take y of omega as common and x of omega as common. H of omega is equal to y of omega divided by x of omega is equal to minus j omega divided by j omega square plus 5 into j omega plus 6. Next one, Laplace transform. RC into d by dt into y of t plus y of t is equal to x of t. Find the impulse response. By taking the inverse Laplace transform, we can get h of s equal to y of s divided by x of s equal to 1 by RC into s plus 1. By taking impulse response of the above function, we can apply the inverse Laplace transform. We can get h of t is equal to 1 by RC into 1 by s plus 1 can be replaced as e power minus t into u of t. Next one, find the output of the system. H of t is equal to u of t. X of t is equal to e power minus 2t into u of t. While we are applying the Laplace transform of h of t, h of s is equal to 1 by s. X of s is equal to 1 by s plus 2. Therefore, h of s is equal to y of s divided by x of s. We can get y of s is equal to h of s into x of s. We can get 1 by s into s plus 2. Now we can apply the partial fraction method, a by s plus b by s plus 2. Now we can get the values as a is equal to 1 by 2, b is equal to minus 1 by 2. Therefore, y of s is equal to 1 by 2 into Laplace inverse of 1 by s minus 1 by 2 into Laplace inverse of 1 by s plus 2. By applying the inverse Laplace transform, we can get the impulse response of the system. Y of t is equal to 1 by 2 into u of t minus 1 by 2 into e power minus 2t into u of t. Next one, we can see the assessment. The system transfer function is given by h of s equal to y of s divided by x of s. That relates the input and output of the system. Differential equation relates the input and output of the system. Fourier transform can be applied for both periodic and aperiodic signals, and it can be represented in frequency domain. What is mean by impulse response? When a unit impulse is applied in the input for LTI system, which can produce the output as h of t. While we taking the inverse Laplace transform of h of s, we can get the impulse response as h of t. Fourier transform of unit impulse function is given by x of f is equal to 1. Laplace transform of unit ramp signal function is given by x of s equal to 1 by s square. LTI systems are characteristics with the help of differential equations, block diagrams, state variable functions, etc. Thank you.